Yes.
Perfect, thanks. So hello everyone, my name is Kalinani and I'm a PhD student at the University of Padua. And firstly, I would like to thank the organizers for giving me this opportunity. And today I'll be talking about some of the recent results from our GRMHD BNS merger simulations. This work has been done along with my supervisor, Dr. Riccardo Ciolfi, and our collaborators, Professor Bruno Giacomazzo, Dr. Wolfgang Castano, Dr. Federico Cipolletta, and Lorenzo Enoggi. So as most of you already know, binary neutron submergers act as a rich laboratory to investigate gravitational waves, short gamma ray bursts, radioactively powered kilonova, and as well as gain deeper insights on neutron star physics. And indeed, the very first detection of gravitational waves from the merger of two neutron stars, that is the GW 1708-17 event, along in tandem with the short gamma ray burst GRB 1708-17A and an electromagnetic transient 8020-17 GFO, has cemented the connection of binary neutron submergers with short gamma ray bursts as well as radioactively powered kilonovae. But this event also left behind some open questions regarding the mechanisms that produce this short gamma ray burst as well as the kilonova. And in order to address these questions, numerical relativity simulations of the merger process play a fundamental role. And in order to incorporate the crucial effects of magnetic fields, we should perform these simulations in GRMHD. So as we all heard from Professor Shibata yesterday, depending on the initial masses and the neutron star equation of state, a binary neutron submerger can lead to collapse to a black hole with or without an accretion disk, either promptly or after a metastable neutron star phase, which could be a supramassive or hypermassive neutron star. And a more extreme outcome could be a stable neutron star that never collapses. Now, according to the leading scenario, this short gamma ray burst central engine is given by this classic black hole disk system, but long-lived neutron stars do remain a likely outcome of these mergers. So one of the open questions our work tries to address is, can this massive metastable neutron star, or the so-called magnetar, act as a central engine to power a short gamma ray burst jet? Also, the kilonova of August 2017 can be modeled at least as a two-component one, having a blue component and a red component. The origin and the mechanism that produced this blue component is still not very well understood. So another open question we try to address with our work is, can the magnetically driven post-merger ejecta that's coming out of this massive neutron star remnant before it collapses to a black hole acts as a source of the blue component of the kilonova. So in this presentation, I will try to cover some of the basic concepts and ideas that emerge out of our BNS simulations performed in GRMHD. And so here you see on top the rest mass density evolution of a merger process in the meridional and equatorial plane for a simulation, that BNS merger simulation that goes up to 100 milliseconds after merger. So something that distinguishes our simulation is this very long post-merger evolution. And in all the simulations that I'm going to talk about, the merger remnant is differentially rotating metastable supramassive neutron star, expected to survive much longer than the simulation timescale before collapsing to a black hole. Below you see the meridional mass distribution on much larger scales of about 3,000 kilometers for a different simulation that extends to about 250 milliseconds after merger. So running such long post-merger evolution allows us to gain some novel insights on how this magnetic field evolves and how it affects the system. So just a quick word on our numerical setup. So we perform these simulations using numerical relativity codes, Einstein Toolkit, and WSKI MHD for binaries having mass ratios of 1 and 0.9 with using a chirp mass that is consistent with that of GW 1708-17. We use the APR4 equation. We use the piecewise polytropic approximation for the APR4 equation of state for the neutron star matter. And as Tanmay talked about, we use this public code core called Loren for producing our initial data. And finally, we add magnetic fields to our neutron stars as internal colloidal fields, having different initial field strengths. And the finest resolution employed is about 220 to 250 meters. So first, let's look at magnetic field evolutions. Magnetic field is strongly amplified due to different mechanisms in action. At merger, first, Kelvin nanomoles instability develops in the shear layer when the two neutron star cores come into contact. And this is taken over by MRI at later stage. So here on the left, you see the wavelength of the fastest growing MRI mode over the grid spacing. And about 30 milliseconds after merger, we see that MRI is almost resolved everywhere, and especially purple region indicates that MRI is covered, the wavelength is covered by about 10 to more than 10 to about 1,000 grid points. So this gives us the confidence that the following MHD evolution and the features coming out at later time are reliable, at least qualitatively. On the right, we have the magnetic energy evolution for our different simulations. And here, the first interesting thing we notice by running longer simulations is this flattening in magnetic energy, which starts after about 50 milliseconds after merger. And we also know that the maximum magnetization achievable in such merger simulations is likely limited to the order of 10 to the power 51 ergs. Next, we looked at the remnant structure. So here we compare the mass distribution on smaller scales for two simulations. One is non-magnetized, and one is a magnetized with an initial strength of 5 times 10 to the power 15 Gauss. And as you can see, in general, the remnant has a nearly spherical core attached to a torus-shaped outer envelope for both non-magnetized and magnetized case. But after a few tens of milliseconds, when the magnetic field becomes dynamically important, we find rather a more isotropic distribution for the magnetized case, while for the structure for the non-magnetized one remains rather similar. Next, we have the rotation profile. So in general, we find that for the magnetized simulation, that the remnant, the general trend we find is that the remnant is a nearly slowly rotating inner core with the faster rotating outer envelope, with the maximum frequency peaking around 12 kilometers from the axis. And for larger distances, we find the profile to be nearly Keplerian. And on the right, we also try to find the effect of magnetic fields on this rotation profile. And we find that for substantially higher initial strength, there is a non-negligible effect on the Keplerian curve. Then we also study the influence of magnetic fields on mass outflows. So here on the left, you see the radial distribution of unbound matter with the radial distance on the x-axis and the time on the y-axis for the magnetized case on top and the non-magnetized case on bottom. And the first thing we notice is that in addition to this dynamical ejecta, which is common to both simulations, we have a substantial contribution by this magnetically driven post-merger winds for the magnetized case. And on the right, you have the rest mass density as well as the magnetic to fluid pressure ratio, also showing that this outflow is rather magnetically dominated. So what happens is, because of this outflow, the funnel along the spin axis also gets baryon polluted, and this could be a problem and be a hindrance when we have to produce a jet at a later time as well. Here let's look at this geometry and structure of the magnetic fields. Here we have the evolution of magnetic field lines close to the remnants, and the first thing we observe is that there is indeed a strong amplification in the equatorial plane, developing a toroidal field with a growing helical growing helical lines around the spin axis, developing a poloidal field, which kind of disrupt towards the end of the simulation. On much larger scales, these field lines extend to more than 100 kilometers along the spin axis, hinting towards an emergence of a global magnetic striae with an average poloidal strength of about 10 to the power 15 Gauss. By the end of the simulation, that was around 100 milliseconds after merger. Now, what if we go beyond to 100 milliseconds? So by the recent simulation performed by Dr. Chalfi, when we go up to 250 milliseconds after merger, jet-like helical structure might emerge thanks to the continuous winding action of the neutron star differential rotation. But this result is not ubiquitous. But in this particular simulation, we notice that a magnetically driven collimated outflow would break out of this baryon polluted environment and reaching radial velocities of about 20 to 30% that of speed of light. However, this outflow does not seem to be compatible with that of Earth-shot gamma ray burst jets, since the maximum achievable Lorentz factors that we find are quite low, and the outflow is at least three orders of magnitude too heavy. So these results favor or disfavor the magnetized scenario for producing a short gamma ray burst jet, and rather favor the black hole disk system as a central engine for the SGRB jet. Now, in another work, we instead look at the origin of the blue component of the kilonova that was so kilonova that accompanied the GW 1708-17, and this kilonova can be at least modeled as a two-component one, having a blue component and the red component, and the blue component peaked around in the UV and blue wavelengths, and is associated with a material having a mass of about 2% that of solar mass, and expansion velocity is about 20 to 30% that of speed of light, and the red component is associated with much relatively smaller velocities and larger mass. While the source of this red component is most likely the baryon wind rising from this accretion disk that eventually forms when the remnant is collapsed to a black hole, the source of the blue component is still not very well clear. So we consider the possibility that the magnetically driven post-merger ejecta that has been given out by this massive neutron star remnant before collapsing to a black hole could act as a source of the blue component of the kilonova. And this has already been suggested in literature as well.
We're reaching the time here.
Right, just a couple of slides, thanks. We analyzed the simulations for our latest simulation. We analyze the results from our data from our latest simulation, and we need to find velocities and unbound mass, ejecta mass, reaching that is consistent with that of the blue component of the kilonova. Just a quick advertisement and jumping topics here. Lorenzo yesterday talked about our GRMHD code Spritz, and recently we have introduced also a quantuplum scheme called the reprimand scheme in Kustown et al. 2021, which seems to be quite a robust and accurate scheme. And we have implemented this currently in Spritz and performed a number of GRMHD tests in 3D. And on the left, you see the magnetic field strength for one of the tests, consisting of a neutron star emitted with this external dipolar field, and showing that the C2P can handle high magnetization, low density regimes rather well. While on the left, we have another test which considers black hole accretion disk system, and here too, for the magnetic field, this C2P can handle magnetized black hole environments rather well too. With that, I stop here. Just a quick comment on the future exploration. So we currently have this GRMHD code, and also the C2P scheme. We want to perform BNS merger simulations using neutrino radiation and using temperature dependent and temperature and composition dependent EOSs, and also include magnetic fields extending out of the neutron star. And that's about it. Thank you very much.
Okay, thank you. Yeah, information-packed talk. And let's see if we have any questions. Okay, Scott.
Yeah, great talk. Thank you. Could you explain the second to last slide with the comparison to I guess my Kondo-Prim routine?
Right. So thank you for the question. I did not have enough time to go through this. So what we did was we embed a neutron TOV with a dipolar field, or using the prescription of Moesta et al. 2020. And we performed the simulation with reprimand as well as noble quantum prim, setting the atmosphere density to about 6 times 10 to the power 4 grams per centimeter cube, if I remember correctly. And when we evolve this with reprimand, it does not crash, and the simulation goes fine until the end of simulation that we stopped is around 10 milliseconds. While for the scheme by Noble et al., it crashes right in the beginning, about after 0.1 millisecond. So only after we increase this atmosphere density by 10 times, we find a stable evolution by Noble, using the scheme of Noble et al. So this is one thing that we find is, okay, reprimand C2P is able to handle rather highly magnetized low density regimes. I hope that answers your question.
Yeah.
Okay.
Thanks.
Julian, if you're speaking, you're muted.
Thank you. Yes. In view of the time, I'd like to move on to the